Everyone, welcome to this live stream where we're going to go over everything you need to get started with Swift concurrency. Before we get started, let me just go on my phone to make sure that I'm indeed live on YouTube. But it seems that I am, because since it happened once in July that I launched a live and something bugged on my software and actually I wasn't live. Since then, I've become a bit cautious, but I can see some of you. Uh, yes. Oh, right. I see people in the chat. I know that you are here. Perfect. Welcome. So as you can see on the thumbnail, in this live stream, we're going to go over all of the main features of Swift concurrency. So I try to sum them up on the thumbnail. You can see some of them behind me. So we'll talk about the async and await keywords. We'll talk about task and task groups, about asynclet, about what Swift concurrency means, and what would be maybe the opposite of concurrency. Is there an opposite to concurrency? We are going to go over all of these things. But for this live stream, I wanted to try a new format because for both my SwiftUI and combined courses, the approach I took was that I prepared some content, some examples, and then I was delivering that content over the course of one or more live streams. And that's an approach that has advantages. Some of you have enjoyed it, but one of the big drawbacks for me is that you only get my point of view. And I feel that when you're trying to learn something new, especially if you want to learn something new quickly and comprehensively, being able to benefit from more than one point of view is really something that helps learn better and even sometimes learn faster. So you will see, if you go in the description of this video or of this live stream, you will see links to 5 articles. And so what I'm gonna do is that I'm going to use as the base, as the content for this live stream, these 5 articles from several content creators from the community. And these articles, they all go over one of the items that I want to explain. And the idea is that my goal is that through this approach, not only will you have my point of view, because I will be commenting and explaining as best as I can, but you will also have the point of view of other people. And I hope that by the end of the live stream, it will deliver a very comprehensive point of view of what Swift concurrency is. So let me have a look at the chat. I see a few people are saying hi. There are quite a few of you in the chat, which is always nice for live streams that are work related. Will I be covering async streams and async algorithm again? I don't think I will go all the way up to async stream. We'll see if there is time. My goal is to go between like 1.5, 2 hours. I don't want to go over 2 hours because then it's too long for someone to realistically watch the replay. So we'll see. I will start with the basics, and if we have time, we will go further, but we will definitely talk about async sequence, of course. I think that's more than enough for the intro. Just remember, if you are watching live, you have the chat. That's a great opportunity to ask any questions or make any remark that you have. When you do so, not only do you hopefully get an answer if I can provide one, but also there is a very good chance that you are voicing the question or the remark that someone watching the replay is having, and so you are giving the people watching the replay a voice during the recording. Okay, so let's get started with the first article I have selected. So it's an article from Antoine van der Lee, so from his blog avanderlee.com. As I said, you have all the links in the description to check out not only this article, but also the blog itself. This live stream is a beginner tutorial, so it's also one of my goals to give pointers to some really great sources of iOS and Swift content, and this blog is definitely one of them. And so this first article is called Async Await in Swift, explained with code examples. So it's really the basics to discover how async await works. So let's get started. So async await is part of the new structure concurrency changes that arrived in Swift 5.5 during WWDC 2021. So indeed, async await and Swift concurrency are already more than 2 years old. So it's no longer the shiny new feature. Now it's been part of the landscape for a couple years. And concurrency in Swift means allowing multiple pieces of code to run at the same time. This is a very simplified description, but it should give you an idea already how important concurrency in Swift is for the performance of your apps. Because of course, if you can only run one piece of code at a time, imagine that you are making a network request. Until the network request has returned, your app cannot do anything, and that also includes responding to user events. So we definitely don't want our apps to freeze while they are making network requests, because especially with modern apps, the apps will be basically like frozen all the time and unusable. And so that's where concurrency comes into play, so that several tasks, several actions can execute concurrently in a way that will feel seamless to the user. So with the new async methods and await statements, we can define methods performing work asynchronously. So at its core, Swift concurrency is really about giving the tools, giving the primitives to deal with asynchronous code at scale. Maybe we will see later examples of how asynchronous code used to be in Swift before concurrency, but historically it was completion handlers, so closures, then combine. But these approaches, either they didn't scale very well, or they required you to learn quite a lot of concepts in order to get started. And we'll see that for the basic use case of asynchronous code, async await is extremely simple and easy to wrap your head around. So you might have read about the Swift concurrency manifesto by Chris Latner before. If you've never read this, I recommend maybe not reading it, but at least checking it out, because it's a very complex document, if I remember it correctly. So if you are new to Swift and you are scared, this is normal. The first time I saw this document, maybe 2 or 3 years ago, it took me some time to read, like go over it, but it's a very interesting read. Just prepare some time. It's not the kind of thing that you can read like in the subway between your job and home. You need to read like dedicate some time and effort to reading it. Many developers in the Swift community are excited about the future to come with a structured way of defining asynchronous code. Now that it's finally here, we can simplify our code with async await and make our synchronous code easier to read. And you will see that easier to read is one of the big selling points of Swift concurrency. The goal is to make asynchronous code almost as easy to read as synchronous code. So what is async? Async stands for asynchronous and can be seen as a method attribute, making it clear that a method performs asynchronous work. An example of such a method looks as follows. So you can see the method in its signature. So it's a function or a method declared with the keyword func, then an identifier, a parameter list, a return type, and we can see, along with the keyword throws, the keyword async. So async is really a characteristic of a method. And what's really great, if you've ever had to deal with code that used either a completion handler or combine, or even Eric Swift for that matter, is that you can see that the async function simply return its result. It was different with a completion handler because the function would take as an argument a closure that would take as its own argument the result of the method, so much more complex than just returning an array of images. And same thing with combine, because it would return maybe a publisher of array of UI image, or maybe a future of array of UI image, but not just the type itself. There would be something more around it. Here we just have the type itself, and besides that additional async keyword, the signature of the async method is exactly the same than the one a synchronous method would have. And that's definitely one of the big features and one of the big selling points of Swift concurrency. So the fetch images method is defined as async throwing, which means that it's performing a failable asynchronous job. And it shows also that you can definitely, a method or a function can be both async and throwing, or can be either only async or only throwing, or neither. One doesn't exclude the other. Async and throwing are completely orthogonal. But the fact that we can use throws with async method is actually something really nice, because if you dealt with completion handlers before, and we will have the example actually just after, but a completion handler, you couldn't throw an error, you had to pass it as an argument. Same thing for Combine, which had to deal with error cases, with publishers erroring out, but you couldn't just use the standard throws and then do catch mechanism. Here with async await, you can do it, and it also eliminates a good amount of boilerplate code. And so this method right here would return a collection of images if everything went well, or it throws an error if something went wrong, as the declaration suggests. So we can see that there is no trick in this declaration. It's very straightforward. Now, let's see how async replaces Clojure completion callbacks, because this is what used to be the go-to solution since the day of Objective-C. Not the beginning of Objective-C, but Objective-C 2.0, or yeah, Objective-C 2.0, I think that was its name, added the support for blocks, which was basically the name of closures in Objective-C, and then Swift had closures, and so many APIs from Apple were designed around passing a completion callback. And so async methods replace the often seen Clojure completion callback pattern. Completion callbacks were common in Swift to return from an asynchronous task, often combined with a result type parameter. The above method, so this one right here, would have been written as followed. So a method called fetchImage, which takes an argument, which is a completion handler, and this completion handler is a function that would take as its argument the result of the asynchronous job. And so here it would be the result type that could contain either the success case with an array of UI image, or the failure case with an error. And we can see that if you have used closures and completion handlers a lot, you probably notice that this is a simplified example, because this is not marked with @escaping, which in reality would almost always have to be. And you know as well as I do that @escaping Clojure, you have the fact that you need to deal with weak self and all of this added complexity. So defining a method using a completion closure is still possible in Swift today, but it has a few downsides that are solved by using async instead. So what are these downsides? So you have to make sure yourself to call the completion closure in each possible method exit. Not doing so will possibly result in an app waiting for result endlessly. And it's actually easier than what you would think to forget to call the completion handler, especially if you have to deal with error cases. It's very easy to forget that there is a code path in which you are not calling the completion handler, and maybe your app is displaying a blocking loader full screen forever. And these kind of issues are really, really, really bad, because the UI of your app is blocked. It's not a crash, so you're not notified in Crashlytics or any kind of crash reporting service. Your support is probably unreachable unless the user kills the app and reopens it, but not all users will be motivated enough to do that. Some of them will just stop using your app, so it's really a bad kind of bug. And a kind of bug that can be also very hard to detect when doing QA. Closures are also harder to read. It's not as easy to reason about the order of execution as compared to how easy it is with structured concurrency, because with a closure you pass a piece of code that will be executed later, but it means that the locality of the code in your source code is no longer correlated with the time when the code will be executed. The code is defined and then executed at a later time, and that makes it harder to reason, because you have to figure out when the code will actually be executed. I hinted about the next item when I talked about escaping closures, but retained cycles need to be avoided using weak references or unowned references. If you use self in a closure that is itself retained by self, then you have a retained cycle. Neither the closure nor self can be released from memory, and so you have a memory leak. If you have too many memory leak, then your app loses performance up to the point where it could even get killed by the system. And memory leaks are really bad because they will almost always degrade the experience for your user, simply because you will use memory that is no longer needed, and especially on lower end devices, it can very easily make your app feel laggy or make your app be killed by the system. So you really want to avoid retain cycles as much as possible. And finally, implementers need to switch over the result to get the outcome. It's not possible to use try-catch statements from the implementation level. That's what I was referring to a little bit earlier. These downsides are based on the closure version using the relatively new result enum, which was introduced with Swift 5, if I remember it correctly. It's likely that a lot of projects still make use of completion callbacks without this enumeration, and so something that looks like this, you pass in two arguments which are both optional, and then inside the method you have to unwrap the two arguments safely, we can hope. But also, the big problem with this approach is that there is nothing preventing you at compile time from calling the completion handler with nil values for both or actual values for the result and the error. And if you do that, it will cause some very weird issues that can be also very hard to detect. And so defining a method like this makes it even harder to reason about the outcome on the caller side. Both value and error are optional, which requires us to perform an unwrap in any case. Unwrapping these optionals results in more code clutter, which does not help to improve readability and also add additional room to make stupid mistakes. But we all know that stupid mistakes tend to find their way into our code bases, no matter the effort we make to avoid them. Basically, if it's kind of like Murphy's law, basically. Anything that can happen will happen, and any state that is not explicitly forbidden by the compiler, you can be sure that at one point or another, you or one of your teammates will be writing code that will fall into this bad state that wasn't supposed to happen, but still happened. So now let's get into the meat of the topic. What is await? Await is the keyword to be used for calling async methods. You can see them as best friends in Swift, as one will never go without the other. You could basically say await is awaiting a callback from his buddy async, which is a very nice way to put it, because even though this sounds childish, it's not a lie. We could take a look at an example by calling our earlier defined async throwing fetch image method. So this is what a call site would look like. So inside the do block, we call the async throwing method. So we have to use both the try and the await keyword. And these keywords, actually, if you ever look at how the Swift compiler is implemented, if I remember it correctly, these keywords, they don't really do anything. Their goal is just to make it very obvious when you read the code that this method call can throw, and this method call can create what Swift calls a suspend point. And this way, it's very easy when you read code, especially if you read code, for instance, in a pull request, to know, okay, this is the line that can have like this, not weird, but this special behavior of either triggering the catch block or having the execution of the code be paused until the async function has returned. It might be hard to believe, but the above code example is performing an asynchronous task. The reason why it might be hard to believe is that when you look at this code, especially if you were doing Swift before the introduction of async await, this looks very much like your regular synchronous code. The only difference is the use of the await keyword, but if you had written code that used either closures or Eric Swift or combine, or even things like NS operation, for instance, this looks extremely simple and much closer to synchronous code than asynchronous code in terms of complexity. And that's because by using the await keyword, we tell our program to await a result from the fetch images method and only continue after a result has arrived. So this is the suspension point that I was referring to. This could either be a collection of images or an error if anything went wrong while fetching the images. So basically, async function, you can see them as regular function that have one special right, is that they have the right of creating a suspend point, meaning that they can pause their execution until their result is ready. And once you have this, we could say a mental model in mind, usually it becomes much easier to reason about this kind of code. So here we are saying that the method fetch message can take some time to finish its execution. That's why we mark it with the keyword await. And we're going to see a little bit later that, of course, as you can imagine, we cannot use the keyword await anywhere in our code, because it's not anywhere in our code that it's okay to pause the execution of the program. Think typically, if you were to pause the execution of the program in application did finish launching, that would probably be a big issue. But I think we're going to go over this a little bit later. So next part is about what is structured concurrency. So structured concurrency with async await method calls makes it easier to reason about the order of execution. Methods are linearly executed without going back and forth like you would with closures. To explain this better, we can look at how we would call the above code example before the structured concurrency arrived. So we're going to see what this piece of code would look like with closures. So it would look like this. First, you call the method fetch image, you pass in a closure as the argument. Thanks to the trailing closure syntax, the syntax is a bit nicer because you don't have to explicitly write the parenthesis and write the argument name. And so you write this code, which will be executed once the result is ready and has been passed as an argument to a call of the completion handler. And what would happen is that first we call the method, then the code below it keeps executing, and at some point, the code inside the closure will be executed. But you can see that it isn't linear, meaning that the code in the middle will, in most cases, be executed after the code at the end. So that's why Antoine means when he says that closures, asynchronous code with closures breaks linearity. Whereas here in this example, this is run first, then this, and it's impossible for this code right here or this code right here to be executed before the first line has finished. So here the code is executed linearly. And as you can imagine, it's much easier to reason about linear code than unstructured code. So as you can see, the calling method returns before the images are fetched. Eventually a result is received, and we go back into our flow within the completion callback. This is an unstructured order of execution and can be hard to follow, especially when you have more than one call site like this. Even more if you are nesting closure calls, meaning that inside the completion handler of a first call, you are making a second call that itself uses a completion handler. And I have memory of apps in the days of Objective-C that had almost up to 10 or 12 nested completion calls in the start of the app, and it was quite something to maintain. Definitely fun times. This is especially true if we would perform another asynchronous method within our completion callback, which would add another closure callback. So actually, exactly what I was saying. You can see now the order of execution. So it's really a great example from Antoine. You can see that it runs like first 1, then 2, then 3, then 4, then 5, then 6. And imagine if you were to have like 4, 5, 6, 7 completion calls nested into each other, then the complexity of the code, the number of code paths that can be, is becoming completely crazy. And at this point, it becomes like impossible to reason about it in a way that is clear. And you can be sure that you will get some weird bugs that will be very hard to anticipate. And the issue is that each closure adds another level of indentation, which makes it harder to follow the order of execution. Rewriting the code above, so this code right here, by making use of async await explains best what structure concurrency does. You can see that first we call the method, then we call the second method, and then the results of this second method can be used, but the code is executed linearly. 1, 2, 3, 4, and 5 are executed always in order. And if you've seen some of my other videos on async await, this is typically the example everyone shows, because this is what really makes it very like palpable what is the advantage of using async await compared to closures. So here, the order of execution is linear and therefore easy to follow and easy to reason about. Understanding asynchronous code will be easier while we're still performing sometimes complex asynchronous tasks. And because if you are thinking, oh yes, but don't worry, I'm only dealing with simple cases, it never works like this. Maybe your app at its beginning, in its first version, maybe will deal only with simple cases, but then there are always new features to develop, and apps basically only ever increase in complexity. And so it's important to have mechanisms that scale well when the complexity increases, because otherwise that's how you end up after 2 or 3 years with a code base that has become unmanageable, and bugs keep appearing and you never see the end of them. So async methods call in a function that does not support concurrency. How do you call an async method at the top level? Because at some point you're gonna have to call an async method from a method that is not async. Think typically, like I was saying, application did finish launching with option, view did load, all of these app lifecycle methods, which are definitely not asynchronous methods. So while using async await for the first time, you might run into an error like the compiler telling you async call in a function that does not support concurrency. So here in this example, we are trying to call an async method from a regular method that is not async itself. This error occurs because we try to call an asynchronous method from a synchronous calling environment that doesn't support concurrency. We can solve this error by either defining our fetch data method as async as well. And once again, before we could see that the async keyword would sit at the same place than the throws keyword. And here we can see a similarity with the error throwing mechanism, because you can either, when your method needs to call a throwing method, you can either just declare the host method as throwing and so propagate the error upwards, or deal with it on the spot. And here it's kind of the same idea. If you need to call an async function, either you can make the calling function async itself, or you can deal with the asynchronous call inside the method, and we'll see the syntax for it just afterward. But it's very interesting to see the symmetry between how these two features work. However, doing so would move the error to a different place. Instead, we could use the task.init method to call the asynchronous method from a new task that does support concurrency and assign the outcome result to a property in our view model. So this is the syntax that you might have seen creating a task. Here you can see it's task.init, but most of the time you can actually omit the init, because the init takes a closure which is async, but you can actually use a trailing closure syntax, and so just call task and then pass in the closure. By the way, this is also an opportunity to see that closures can also be async, which kind of makes sense because closures could be throwing, so there is no reason for a closure not to be able to be also async. And here you can see that this time the function fetch data is not async, it's a regular synchronous method defined inside an observable object. And what we do is that inside this method, we create a task which creates an asynchronous execution environment in which we can call async methods. And so in the async closure we pass to the task, so in the code that the task will execute, we call the fetch image. And what we do is that we assign its result to the published property we have defined inside our content view model. And so this is a typical example of how you would trigger an async call from a SwiftUI app. Typically, we can imagine this method fetch data will be called on the onAppear of the view. And so it will trigger this task, which will run this async function. And in turn, it will set the result of the async function to this property of the view model. And maybe you might be thinking instead of like threading, how is threading working in this example? We'll see if it's covered later. If it's not, I will go back over it before we go to the next part. I see a great question in the chat from Omar. Can async await replace combine and vice versa? I would say that async await implements a subset of what combine does. Combine allows you to process values over time. Async await is more towards how to make a single asynchronous call that will return a single value. You have ways with async await to deal with values over time through a package called called async algorithms. Sorry. So my take would be use async await by default. And when you reach a point where your use case can no longer be solved efficiently by async await, then look at combine. But if you're creating a new iOS app today, for instance, to implement a network call, I wouldn't recommend using combine because async await and Swift concurrency is much better at this. So short answer, async await and Swift concurrency implements an alternative to combine. It doesn't handle the most complex use cases, maybe not as well as combine does, but for the simpler use cases of writing async code, async await, I would say, is a better alternative to combine. At least that seems to be the direction that Apple is going into when you see that the new API almost always use Swift concurrency instead of combine. And so using the async method, there is something wrong with this sentence. But basically, using the async method inside this trailing closure we pass to the init of task, we create an environment in which we can call asynchronous methods. The fetch data method returns as soon as the async method is called, after which all synchronous callbacks will happen within the closure. So what's important to understand is that this will create a task, but the function fetch data will keep executing. And so here, since there is no other instruction inside the method after creating the task, the method will return and the rest of the code will keep executing. And this allows me to explicit one of the big like design choices of Swift concurrency, which is that tasks are what we call fire and forget, in the sense that when you create the task, it will keep executing until it's finished. And if you don't need to cancel it, if you don't need to have code that cancel it, you can just fire the task and forget about it. So you don't need to keep a reference to it. You don't need to store it into any cancelable. It will automatically be destroyed once it has finished executing. By the way, creating a task is not structured concurrency. Creating a task, an explicit task, is what's called unstructured concurrency, in the sense that at this point, we are our code no longer reads linearly. We are creating a point where we have a new execution context. So the name Swift concurrency, it can be a bit tricky because when we refer to concurrency, sometimes we say that because we mean async await. But if you look at the spec of the language, you will see that you actually have structured. Oh, I'm sorry. I made a confusion between Swift concurrency and structured concurrency. Sorry, I will restart this part of the explanation. So when you create a task, you are doing what's called unstructured concurrency, because when you create a task, you create a new execution context that will execute independently from its call site. However, we also have structured concurrency, and we will see a little bit later examples of structure concurrency. And both structure concurrency and unstructured concurrency are part of Swift concurrency. That's the explanation I wanted to make. That's the point I wanted to make. You're saying Pixel Science, weird code syntax. Why not use task without init? Most of the time, this is what you would do. Here, I guess the goal is to make it clear that actually task is not a magic. Actually, the goal here, I think, is to show that task is not magic and task is not a keyword of the language. It's a type that we can create through an init. So I think the choice here is to make that explicit, even though, as you said, you don't write the dot in it most of the time. So here, I think it's more for explanation, for pedagogical purposes. Okay, let's keep going. So adopting async await in an existing project. So when adopting async await in existing projects, you want to be careful about not breaking all your code at once. When performing big refactors like this, it's good to think about maintaining all implementations for the time being, so you don't have to update all your code before you know whether your new implementation is stable enough. This is similar to deprecating methods in an SDK, which is used by many different developers and projects. It's a very good point that Antoine is making, because I've seen examples where you would migrate to async await, and then somewhere in the low level of your code, or maybe of some third-party frameworks, there is some code that does asynchronous code in a way that it shouldn't really do it, and it actually breaks some expectations of Swift concurrency, and your code crashes in production, and it can be very frustrating. So I can definitely concur on the fact that when you do that kind of migration, you want to do it progressively, and if possible, have both implementations stay together for some time, so that you can progressively roll out the new implementation to your users to make sure that nothing is crashing in unexpected ways in production. Obviously, you're not obligated to do so, but it can make it easier to try out async await in your project. On top of that, Xcode makes it super easy to refactor your code, and also provides an option to create a separate async method. So if you have a method that uses a completion handler, you can indeed do a right-click refactor convert function to async, and it will generate an async version of your function. And we will see in the next article what are the functions that you call under the hood to turn a completion handler based function into an async function. And by the way, since the release of Swift 5.9 and macros, there are also macros that exist in order to create either an async version of a completion handler based function, or a completion handler based version of an async function. And basically, if you have one of the two, you can always create the other, because it's very easy to bridge the two worlds together. So each of the refactor methods, so convert function to async, add async alternative, or add async wrapper, has its own purpose and results in different code conversions. To understand better how it works, we'll use the following code as refactor input. So let's imagine that we have this fetch image asynchronous method, which uses a completion handler to provide its result. So if we do convert function to async right here, this first refactor option is going to convert the fetch images method into an async variant without keeping the non-async alternatives. So it will remove the existing one and create a new one. It will be useful if you don't want to maintain your old implementation, and the resulting code looks something as follows. And then the implementation will depend on what you had in your original method. The add async alternative, it will make sure to keep the old implementation in place, but does take care of adding an @available attribute. So it will basically add this @available to say that this method, so fetch image completion, is deprecated and is been renamed to fetch image, so that there will be warnings, deprecation warnings in code that uses this method. And we'll see a little bit later how this new async variant is implemented. So the available attribute right here is useful to know where you need to update your code towards the new concurrency variant, though the default implementation Xcode provides does not come with any warning since it's not marked as deprecated. To do so, you'll need to adjust the available marker as follows. So you need to add a deprecated, you can see it's not present right here. You need to add the deprecated attribute so that you actually get the warnings. Then a link to an example about the available marker, which I definitely recommend for you to read after you finished watching this video. So the benefit of using this refactor option is that it allows you to progressively adapt to the new structure concurrency changes without having to convert your complete project at once. This is even more important if you are shipping an SDK, because you cannot expect all of your users to implement breaking changes to your API overnight. So building in between is valuable so that you know that your code changes work as expected. Implementation that make use of the old method will get a warning as follows with a suggested fix to migrate to the new async version. And so with this, you can progressively change implementations throughout your project and use the provided fix button in Xcode to automatically convert your code to make use of the new implementation. Of course, since the new implementation is async, you will still need to adapt your code in order to be able to call an async function from a place where it's probably not possible. And so remember, you will have two choices then to do it. Either make the calling function async itself or create a task. And finally, last option, to add an async wrapper. So the final refactor method will result in the easiest conversion since it will simply make use of your existing code. So it will wrap your existing code into an async wrapper through the use of this method with checked continuation, which we're going to see in details, in more details later. But you can see here as an introduction that the newly added method makes use of the with checked throwing continuation method, which was introduced in Swift to convert closure-based method without much effort. So it's really what allows us to bridge these two worlds. Non-throwing methods can make use of the with check continuation, which works the same but does not support throwing errors. These two methods suspend the current task until the given closure is called to trigger the continuation of the async await method. In other words, you'll have to make sure to call the continuation. So this argument right here, don't worry, we'll go into details just a bit after. This is quite a complex topic, so we'll go into all of the details. But the gist of it is that you'll have to make sure to call the continuation closure based on the callback of your own closure-based method, and this is what will allow the async with check throwing continuation method to return. But we'll go into it into more details just after. So how do you pick the right async await refactor method for your project? These three refactor options should be enough to convert your existing code into async alternatives. Depending on the size of your project and the amount of time you have for the refactor, you might want to pick a different refactor option, though I would strongly advise progressively applying changes since it allows you to isolate parts that change, making it easier to test whether your changes work as expected. Solving the reference to captured parameter self in concurrently executing code error. So another common error when working with async method is the following one: reference to captured parameter self in concurrently executing code. This basically means that we're trying to reference an immutable instance of self. In other words, you're likely referencing either a property or an instance that's immutable, for instance, a structure like in the following. So we have a struct, which is a content view model. It has a property, an array of images. And in the init, we create a task. And that task, we want for its result to set the array of images. But we have a problem because we're trying to mutate self. And in Swift, I don't think you are allowed to call a mutating method on a reference to self captured inside a closure defined inside self itself. That's a lot of self, and it shows how complex this problem seems to be. And this error can be fixed either by making your properties mutable or by changing the struct into a reference type like a class. So if you need to update your view model in response to the result of an async call that you trigger through a task, indeed, most of the time you will be using a class. Thinking about it, I think I've mostly used this when I was inside view models in SwiftUI, and they were classes, and or either in UIKit. But in UIKit, both view controllers and view models will almost always be classes also. So if you have this error, basically, like I guess most of the time the solution will be indeed to turn your struct into a class, which kind of makes sense because even with SwiftUI, in SwiftUI, views are structs, but data sources are classes. Will async await be the end of the result enum? That's an interesting question because the result enum was added mostly so that closures would get a little bit more type safe. So let's see what's the opinion of Antoine. So we've seen that async methods replace asynchronous methods that make use of the closure callbacks. We could ask ourselves whether this will be the end of the result enum in Swift. In the end, we don't really need it anymore as we can make use of the try-catch statements in combination with async await. The result enum won't disappear anytime soon as it's still being used in many places throughout Swift projects. However, I won't be surprised to see it being deprecated once the adoption rate of async await is getting higher. Personally, I have not been using the result enum in any other place than completion callbacks. Once I'm fully using async await, I won't be using the enum anymore. And it's true that I don't remember using the result enum nearly as much as I used to since I've been using mostly async await to deal with asynchronous code. One thing to note though is that there is quite an interesting difference between how the result enum works and how the throwing mechanism works. Is that the result enum, when you use the result enum, your errors are statically typed, meaning that you need to provide the actual type of the error, and you can provide a type more specific than just the protocol error. However, the throwing mechanism in Swift is not type checked, in the sense that you can only throw something that conforms to error, but you cannot say that your function only throws a specific kind of error. There are very good reasons for it because it makes it much easier to compose throwing functions together. But it's one of the main difference of using the result enum to convey an error or using the native built-in throwing mechanism. But I agree with Antoine, most of the time the built-in throwing mechanism is more than enough for the problems I need to solve, and so I haven't used the result enum nearly as much. But I see a very interesting comment in the chat saying that I still use a result in all of my combined code. Let me show the comment where it's more visible. I still use results in all of my combined code. I prefer publisher with result output and never error types. That's true that in the context of combine, using result is nicer because it removes the error. I mean, it makes the error case just a regular value, which can be nice because when the publisher errors out, it also finishes in combine, which many times is not what you want. So it's basically kind of like the materialize function in Eric Swift if you've ever used it. But that's indeed a very interesting remark. And I didn't know that type throws are pre-pitched on the Swift forums. When I have time, I will go and check it. It's interesting to see Swift make that switch. And so we've reached the end of the first article. It took a bit more time than I thought, but I think this is the longest one of the 4 articles. But I picked it because it's really an excellent introduction to async await. So we will be moving to a different article from a different blog. But if you want to keep learning more about async await, I really recommend these articles from Antoine's blog. And in general, I really recommend Antoine's blog and also his newsletter that he sends every Tuesday, which is a great way to stay up to date with the recent articles that were published by the iOS community. So I definitely recommend that you check it out, and you have the link to the article in the description of the video. Finally, let's read the conclusion. So async await in Swift allows for structure concurrency, which will improve the readability of complex asynchronous code. Completion closures are no longer needed, and actually I don't think I've ever written one voluntarily since async await has been released. Sometimes you don't have a choice because you are dealing with legacy code, but voluntarily, I don't think I've ever written a closure anymore. And I've definitely not written any new API that would use a closure as a way to return its result. So completion closures are no longer needed, and calling into multiple asynchronous methods after each other is a lot more readable. Several new types of errors can occur, which will be solvable by making sure async methods are called from a function supporting concurrency while not mutating any immutable references. And these errors, they are more like, the errors you encounter when you are like getting started, but it's not errors that should happen once you are a seasoned Swift concurrency developer. And also it's errors that happen at compile time, so very different from errors that would arise at runtime. That's all for the first article. Let's move to the second one, which is on the blog of Donny Valls, another very good source of content on iOS and Swift. And this article is about how to wrap asynchronous code in async await. So this article goes into more detail about how this whole continuation business works. So let's go into it. So Swift's async await feature is an amazing way to improve the readability of asynchronous code on iOS 13 and newer. Actually, iOS 13, yes, because that's a very interesting point to mention, because when async await was released, I think it was released with iOS 15, and so you had to have a minimum target of iOS 15 to use it. That was when it was released, announced in June and then released in September. And then in December of that same year, so December 21, Apple backported actually async await all the way to iOS 13, which was a very good surprise, a really nice Christmas gift, because at the beginning it was like, oh, it's the shiny new thing that we cannot use yet, and then we were able to use it earlier than expected. It might be one of the only times that Apple was able to do this kind of late backport, and it was a really good surprise. And nowadays, iOS 13 Plus has become something that is very reasonable as a minimum requirement target, because as of the moment we are doing this live, iOS 17 has just been released something like a week ago. For new project, this means that we can write more expressive, more readable, and easier to debug asynchronous code that reads very similar to synchronous code, what we've just seen. Unfortunately, for some of us, adopting async await means that we might need to make pretty significant changes to our code base if its asynchronous APIs are currently based on functions with completion handlers. So how do we deal with this bad but existing legacy code? I shouldn't call it bad, because when it was written, closures were basically the only option possible. But of course, with hindsight, this code looks kind of bad. What's your minimum iOS target? Good question. So for the app that I work on, we support current and -1 version. So we are in the process of dropping iOS 15, and so we will support iOS 16 and 17. And which version of Xcode and macOS would you use for iOS? I'm not sure I understand the question. If it's the version of macOS that supports concurrency, I have no idea, because I have never developed anything for macOS. So Xcode 3.2 is really old. It would be something like Snow Leopard old. Yes, that's definitely before Lion. So yes, definitely Snow Leopard. So in the case where we have this kind of legacy code, luckily, we can leverage some of Swift's built-in mechanisms to provide a lightweight wrapper around traditional asynchronous code to bring it into the async await world. In this post, I'll explore one of the options we have to convert existing callback-based asynchronous code into functions that are marked with async and work with async await. So how do you convert a callback-based function to async await? Callback-based functions can come in various shapes and forms. However, most of them will look somewhat like the following example. So a function that does something like providing a valid token. It takes a completion handler, which is at escaping, and is called with a result, which can be either a token or an error. And inside this method, we create a URL, then we create a data task, which is itself an asynchronous API that uses yet another completion handler. And then, as you can see, in all of the code paths, we call the completion either with a failure when something failed, or with a success when everything went as it was supposed to, or rather as it was expected to. So the example above is a very simplified version of what a valid token method might look like. The point is that the function takes a completion closure. It has a couple of spots where this completion closure is called with the result of our attempt to obtain a valid token. So if you want to learn more about what escaping is and does, take a look at this other blog post that Donny has on his website. The easiest way to make our valid token function available as an async function is to write a second version of it that's marked async throws and returns a token. Here's what the method signature looks like. So func valid token, async throws, and it returns a token. So it's what we've seen before. This function looks like a regular synchronous function, except that it's marked as async, but it can just return its return value instead of having to provide it through this cumbersome completion handler right here. This method signature looks a lot cleaner than we had before, but it's entirely expected. The tricky part now is to somehow leverage our existing callback-based function and use the result token error that's passed to the completion as a basis for what we want to return from our new async valid token function. To do this, we can leverage a mechanism called continuations. There are several kinds of continuations available to us. There are 4 of them actually, with checked throwing continuation, with checked continuation, with unsafe throwing continuation, and with unsafe continuation. As you can see, we have checked and unsafe continuations. To learn more about the difference between these 2 kinds of continuation, take a look at this other blog post from Donny. The bottom line is that you are supposed to call the continuation only once, and calling it 0 times or more than 1 is a programming error. And what will happen is that with a check continuation, the compiler will add code that will make sure that you are indeed calling the continuation exactly once, and will trigger a crash if you're improperly calling the continuation. But with the unsafe continuation, it will not happen, and so you will not be aware of it until your app crashes. So rule of thumb here is always use the checked version. Always use the checked continuation. The unsafe continuation is only in the rare case where you are wrapping low-level performance-intensive code, but basically I've never had the use case where I had to use an unsafe continuation. So use a checked continuation unless you can prove by profiling your code that there is indeed a significant difference between using a checked and an unsafe continuation. You'll also notice that we have throwing and non-throwing versions of continuations. These are useful for exactly the situations you might expect. If the function you're converting to async await can fail, use a throwing continuation. If the function will always call your callback with a success value, use a regular continuation. This way, it will simplify your code, and you will not have to deal with a potential error case when your completion handler is actually not throwing. And the reason why you have these 2 functions is that because you are wrapping a closure, you cannot use the rethrows keyword of Swift, which is a very convenient keyword that you can apply to a closure, and that will say that the function using the closure will only throw if the closure itself throws. But with closures, with completion handlers closures, since they cannot use the throwing mechanism to trigger an error, you cannot use rethrows, and so that's why you need to have these 2 alternatives if you don't want to have to deal with the error case even when no error is possible. Before I explain more, here's how the finished valid token looks like when using a check continuation. So remember, here we are implementing a wrapper around the existing function, meaning that we keep the existing function that uses the completion handler as it is, we assume it's working as it should, and we're going to wrap it so that it becomes usable from the async await world. So again, if you want to learn more about the difference between unsafe and check continuation, you have the article from Doniz, which I also recommend that you read. But if we go deep into this, into the analysis of this code, we can notice that we can return try await with checked trying continuation. The return type for the continuation will be the type of the object you pass in the resume returning method call. So you can really see it as calling resume on the continuation is what will unblock, will unsuspend this call site right here. And so what you pass as an argument to the resume function will either be returned by with check throwing continuation or thrown by with check throwing continuation, depending on whether you call resume returning or resume throwing. Because the valid token version that takes a callback calls my callback with a result of token and error, Swift knows that the success case of the result argument is a token, hence the return type for with check throwing continuation is token, because that's the type of the object passed to resume returning. So this is just basic type inference. The with check throwing continuation and its counterpart are all async functions that will suspend until the resume function on the continuation object is called. Now you understand why I was saying that you need to call resume exactly once, because if you never call it, you will await forever. And if you call it more than once, it will do something very weird and very undefined with the execution flow of your application. Where were we? We were here. So this continuation object is created by the with continuation function, and it's up to you to make use of it to eventually resume execution, either in the closure if you are in the completion handler, if you are dealing with a completion handler, but you could also wrap, for instance, a delegate that returns one result at some point. And so in that case, you will need to store the continuation and call it once the delegate method has been called. Not doing this will cause your method to be suspended forever, since the continuation would never produce a result. The closure that you pass to the with continuation function is executed immediately. So this closure right here, so it's executed immediately, similarly to the closure we pass to the task.init, initializer, which means that the callback-based version of valid token is called right away. Once we call resume, the caller of our async valid token function will immediately be moved out of the suspended state it was in, and it will be able to resume execution. So this continuation, you can see, it's really what bridges the completion handler world and the async world. And the continuation, you call it from within a completion handler, and by calling it, you unblock the function that was being awaited. And so with this in mind, this bridge, this role of a bridge that the continuation has should be much clearer right now. Because my result can contain an error, I also need to check for the failure case, and in that case, you call resume throwing the error. If we want the async valid token function to throw also the error. And the code above here is pretty verbose, but it can be simplified because the Swift team recognized that the pattern above might be a pretty common one. So they provided a third version of resume that accepts the result object. So you don't need to write the switch yourself. You can just pass the result. And as you can imagine, this method inside of it is just doing the switch and calling the other two overloads of resume. And here's what the call looks like. And this is what the typical code that wraps an asynchronous completion handler based function looks like. And so now you can understand why I was saying earlier that there exist macros in Swift that can produce this wrapper. It's because if you have the name, if you have the signature of the completion handler function, the process of creating the async wrapper is entirely deterministic. You can write an algorithm that from the signature of the signature, yes, that you can write an algorithm that from the signature of the completion handler version will generate the code of an async wrapper. This process is 100% deterministic, and it's much cleaner, especially the call site where we will be calling the valid token method. There are two important things to keep in mind when you're working with continuations. First, you can only resume a continuation once, and even exactly once, so not zero. Zero is an invalid case. And you are responsible for calling resume on your continuation from within your continuation closure. Not doing so will cause the caller of your function to be awaiting a result forever. It's also good to realize that all 4 different variants of with continuation functions make use of the same rules, with the exception of whether they can throw an error or not, or of whether they are checked or not. The usage of these functions is identical. That's also why it can be very easy to, by mistake, use with unsafe continuation instead of with check continuation, because the API will be exactly the same. The only difference will be the name of the function, but substitute with check continuation by with unsafe continuation, and it will not trigger a completion error or a warning. So actually, you might want to have probably a linter that would give you a warning in case someone is using by mistake the unsafe version. I'm pretty sure that SwiftLint or SwiftFormat must have rules for that. I haven't checked, but I'm pretty sure they must have rules for that. Or if not, it might be pretty easy to create one. And so in summary, for this second article, which was much shorter than the previous one, but that makes sense because it was more focused on a specific problem. In this post, you saw how you can take a function that takes a callback and convert it to an async function by wrapping it in a continuation. You learn that there are different kinds of continuations and how they can be used. Continuations are an awesome way to bridge your existing code into async await without rewriting all of your code at once. So you don't have to rewrite your code, but if there were bugs in your initial implementation, these bugs have not gone away by magic. They are still here. It's just a different way to call an existing function. I've personally leveraged continuations to slowly but surely migrate large portions of code into async await one layer at a time, and I can definitely say that I share the same experience. I've used it, and my colleagues have used continuations a lot. Being able to write intermediate layers that support async await between, for example, my view models and networking, without having to completely rewrite networking first, is awesome, especially when your networking code has been extensively tested and you are confident that it works as expected in production. Overall, I think continuations provide a really simple and elegant API for converting existing callback-based functions into async await. I couldn't agree more, and it's also a very good example of software design and how you can design new APIs that makes it easy to adopt a new convention, a new feature, without having to throw to the waste bin legacy code that was already implemented using previous conventions. So it can be very useful to have that in mind, especially if you are writing SDKs, because SDKs are the typical places where this kind of situation would arise. I see a question in the chat. Would you say that async await is better for SwiftUI while Combine is better for UIKit? Honestly, you can use async await with UIKit. It also works very well. In the app I work on, we use async await with UIKit a lot. And so, yeah, I would definitely say that async await is better as the go-to solution regardless, and only use Combine when you don't have choice. Either because you're using some existing code that uses Combine already. But if you can use async await for simple stuff, it should be much easier. Just make sure that you learn about what the main actor is. This is what will allow you, in the context of Swift concurrency, to make sure that your code that touches your UI is indeed running on the main thread. I'm not sure we're going to cover this in this live stream, but I have a video on my channel which is called, I think, Understanding What Main Actor Does in 90 Seconds. So I can only recommend that you check it out. Let's move on to the third article. So I have 5 articles ready for you. So we are at the middle. Another article from Antoine, which is about async let, because async let is really a great feature of Swift concurrency and of structure concurrency. It's what allows you to call async functions in parallel with a very simple syntax. You don't have to create explicitly tasks to run code in parallel. It will be done automatically for you through an incredibly simple and elegant syntax. So async-let is part of Swift concurrency framework and allows instantiating a constant asynchronously. The concurrency framework introduced the concept of async await, which results in structure concurrency and more readable code for asynchronous method, what we've seen before, and you can see a link to the article we went over just before. So how to use async-let? When explaining how to use async-let, it's more important to know when to use async-let. I'm going to take you through code examples that make use of an asynchronous method to load a random image. So we have a method called loadImage, takes an integer, and then it's making a network call that it seems is going to return a random image. I don't know this website, but I would assume that this is what it does. It returns a random 200 by 300 image. Okay, we can see this code uses the new API of URL session, which are compatible with async await. So this API right here, so URL session.shared.data for request. Without async-let, we would call this method as follows. So we would, inside our regular function, create a task, what we've seen before, and then do let first image, await load image index 1, let second image, await load image index 2, etc. So this is fine, but there is a lot of room for optimization, and I guess the article is going to discuss it just below. Because with this code, we tell our application to wait for the first image to be returned until it can continue to fetch the second image. So code is happening sequentially, and the second image won't finish loading until the first one has finished, even though there is nothing preventing the second image and the third image to start loading while the second and the first one are already loading. Like the loading of the second image doesn't depend on the value returned by the loading of the first image. So all images are loaded in sequence, and we will always see the following order being printed out in the console: finish loading image 1, image 2, image 3, because there was this print statement right here. So this is what we want, at least, no, not this is what we want. At least this code has the advantage of being very predictable. It will always run in the same order, but that comes at the cost of an obvious performance improvement that for now is not being realized. So at first, this might look just fine. Our images are loaded asynchronously, and we end up with an array of images that we could use to display in a view. However, it would be much more performant to load the images in parallel and benefit from all the available system resources, because a modern iPhone is definitely capable of running more than one network request at a time. It's actually even better to do so, because from what I understand, waking up the modem has a cost in battery life, and so the more you can group network calls together, the better. There is kind of like an economy of scale on that part. But of course, like with all optimization, that's the big picture idea. The devil is always in the details when it comes to code optimization. And this is where async-let comes into place. So you can see it looks just like this. Instead of saying let, we say async-let. You can notice that the await keyword has disappeared from the call site of the load images. So that's interesting, because up until now, we've seen that a call to an async function would always be accompanied by the await keyword. Here it's no longer the case, but at least we still have an async keyword that is nearby. And the await keyword has moved to the creation of the array. So let's see the explanation for this piece of code. There are a few important parts to point out. First, our array of images now needs to be defined using the await keyword, as we are dealing with asynchronous constants. So before, there was no await keyword on the creation of the array. Now there is one. However, the constants have now become asynchronous. And what's important to understand is that the execution of these asynchronous function will start as soon as we define the async let constant. So you can really see this as creating a task, an independent task for each of the calls, and then here awaiting for all three tasks to have finished and retrieving their result, their returned value. So this is what async-let does. It's basically a very simple syntax to create tasks implicitly. But as you can imagine, since you need to create an explicit constant, it only works for the case where you have a static number of calls to make. If we had been given as input an array of indexes, we could not have used async-let to make parallel calls for each indexes in the array. In that case, we would have had to use a task group, and we will see a little bit later what it is. But async-let, it's a very convenient syntax to run a static number of asynchronous tasks in parallel. And what do I mean by static? I mean that you must be able to explicitly declare a variable to store the result, and so the number of tasks that you will be running, the number of implicit tasks that you will be creating, has to be known at compile time, because you need to define one constant for each of them. And execution will start as soon as we define an async-let. So you could think, looking at this code, that execution starts here when you are awaiting for the result, but actually no. Execution starts as soon as the async-let is created, and then when you await, it will wait for the result if the result has not arrived yet at that point. Here it's probable that it will not have arrived, but if there had been a lot of code between the async-let and its actual usage, it could be very possible that the async-let would have had time to finish. But it's very important to understand that execution starts as soon as the async-let is defined, because as I was saying, this await keyword might make it seem like it's at this moment that the tasks are started. It's not the case. The tasks are started as soon as each asynchronous constant has been defined. So the last point basically means that one of the images could already be downloaded by your app before it's even been awaited in the array. What I was saying, in this case, is just in theory, as it's likely that your code executes faster than the download of the image. But there could be extra code in the middle, or you could be running a mocked version of your underlying service and return some hard-coded image. So running this code will now show a different output in the console. It could be different every time you run the code, because now the three calls are running concurrently, and so there is no longer a predetermined order in which they will complete. But it's not a problem, because your code doesn't depend on a predetermined order. Your code doesn't rely on the order of the task completing being deterministic. It doesn't matter that they can finish in any order, because in the end you're just gathering all the data together and putting it into an array. It could be different every time you run the app, as the order depends on the request time needed to download the image, so something that is unpredictable by definition. So when to use async-let? Async-let should be used when you don't need to see the result of the asynchronous method until later in your code. You should use await instead if any following lines in your code depend on the outcome of the async method. Because indeed, as you can imagine, if second image were to need first image to be passed as its argument, then you would need to use await to use first image, and it would destroy the benefits of using async-let. So async-let, it's useful when you can run calls concurrently, because the calls are independent. Call number 2 doesn't depend on the return of call number 1. When that's not the case, even though you could still write async-let, it would be kind of beside the point, because you would then only be adding extra syntax and making your code actually more complex and more confusing than it need to be. Can you declare async-let at top level? You might wonder if the following code is valid in Swift, so declaring an async-let as a property stored inside a class. Unfortunately, the compiler will show an error. Async-let can only be used on local declarations. In other words, you can only use async-let on local declaration within methods or within functions or within closures, but not at this top level right here. And that's all for the discovery of async-let. So remember, async-let, it's when you want to run independent asynchronous calls concurrently, and there is a static number of them, meaning that you can create one constant for each of the returned value. Now, for the next article, we are going to move to a blog that I'm sure you stumbled onto at one point or another. So we are on Swift by Sandel, John Sandel's blog, which was probably one of the biggest, which is one of the biggest iOS blogs, and probably the first one to reach this kind of critical size, like what John managed to do around like 2017, 18, and 19 was impressive and basically like unprecedented for the time. So there is content about lots of things on this website. I would especially recommend the Discover page. Let me show you, where you have like it gathers like articles, for instance, about concurrency, but there is like explanations, and it gives the article like in a good sense of progression. So it's not just like a list of links, it's really like kind of like a guide, and I can really recommend that you check it out. But for this live stream, I picked an article that focuses on the role tasks play within Swift concurrency system, because we've used tasks up until now, but they were used kind of like, a bit like a joker. When you're like, okay, I need to call an async function, what am I going to do? I'm going to create a task because it's very convenient. But as you can imagine, convenient APIs also tends to have like some drawbacks. And so I wanted to read this article with you in order to make sure that we all understand very well what a task is, and so that we basically like only use a task when we need to, and we don't use tasks incorrectly, and we are aware of the pitfalls that come with them. So when writing asynchronous code using Swift's new built-in concurrency system, creating a task gives us access to a new asynchronous context in which we are free to call async marked APIs and to perform work in the background. So the typical use case we've had for tasks up until now. But besides enabling us to encapsulate a piece of asynchronous code, the task type also lets us control the way that such code is run, managed, and potentially cancelled. I'm seeing that I'm covering the code a bit, and I've been told recently that it can be a bit annoying when you are watching the live or the replay. So let me move the code. Okay, I think this should be safer. Perfect. So bridging the gap between synchronous and asynchronous code. Perhaps the most common way to use a task within UI-based app is to have it act as a bridge between our synchronous main thread bound UI code, because as I'm sure you already know, you are only allowed to touch your UI in iOS on the main thread. This way it solves all concurrency issue. But of course, if you attempt to update the UI from a background thread, your app will probably be killed in most cases, or it will do something very weird and undefined. But most of the time, your app gets killed because that's a way for iOS to enforce quite violently, but still to enforce that there is no undefined behavior on the UI of your app. And think about it, it's still quite important. You don't want the UI of your app to behave in an undefined way, especially if your app is doing stuff that is like very serious, like showing like banking information, or even just showing you like a ride and then showing a wrong information about the driver, these kind of things. So where was I? I think I read this sentence. Yes. So as a bridge between our synchronous main thread bound UI code and any background operations that are used to fetch or process data that our UI is rendering. So typical flow would be user triggers an action that triggers some asynchronous code that needs to run asynchronously, and once it's over, we want to display the result of this asynchronous job back to the UI. For example, here we're using a task within a UIKit-based profile view controller. So there was a question before, is async await working well? Is Swift concurrency working well within the UIKit world? Here we are having an example. To be able to use, so here we're using a task within a UIKit-based profile view controller to be able to use an async marked API to load the user model that our view controller should render. So you can see typical example, inside view will appear, we need to call this API right here, which is async. And so since view will appear is obviously not async, and we cannot turn it into an async function because then it would be a different function and UIKit would not call it, we create a task so that we can make the network call and then assign its result here to a local variable and then call the method user.didLoad, which will probably update this user property right here. So one thing that's really interesting about the above code is that there are no self-captures inside this closure here, nor are there dispatch queue main async calls, no tokens or cancellables that need to be retained like Combine or RX Swift would require, or any other kind of bookkeeping, what I often call boilerplate, that we normally have to do when performing asynchronous operations using tools like closures or Combine. So how exactly are we able to perform a network call, which is definitely going to be executed on a background thread? Otherwise, we would notice because our UI would basically stop working for some amount of time. And then directly call UI updating methods like user.didLoad and handle error without first manually dispatching those calls using dispatch_queue.main. This is where Swift's main actor attribute comes in, so what I was referring to a bit earlier, which automatically ensures that the UI-related APIs, such as those defined within a UI view or UI view controller, so you will see that UI view and UI view controller are both annotated with @main_actor, are correctly dispatched on the main thread. So as long as we're writing our asynchronous code using Swift's new concurrency system, and within such a main actor marked context, such as a subclass of UI view controller, then we no longer have to worry about accidentally performing UI updates on a background queue, which is one of the very cool and powerful features of Swift concurrency. But be careful, it only works, as John is saying, in concurrency code. So if you are writing code in a regular closure or in Combine, the @main_actor annotation will be completely ignored. So it can also give you a false sense of security that you definitely don't want to have. And also think that you could have some code in some lower level of your app or even in third-party frameworks that could be using closures or other async mechanisms that do not use concurrency. And this code would not benefit from the @main_actor annotation. So be careful if you are passing UIKit objects to code that you don't have knowledge of what's happening under the hood, because it could result in some crash at runtime. Another thing that's interesting about our above implementation is that we're not required to manually retain our loading task in order for it to complete. So what I was mentioning earlier, that tasks are fire and forget by default, that's because asynchronous tasks are not automatically cancelled when their corresponding task handle is deallocated. They just keep executed in the background. And if you want to cancel a task, then you will need to keep the handle of the task around in order to be able to call cancel on it. I don't think we will cover this part in this live because canceling a task is getting into the more advanced use cases, but you can definitely find articles on how to cancel a task, and in the description you have a list of great blogs where you are very likely to find such an article. Now referencing and actually no, it comes just after. So I should have just read instead of starting into like saying stuff, because the next part is about referencing and canceling a task. However, in this particular case, we probably do want to maintain a reference to our loading task, since we might want to cancel it when our view controller disappears. And we probably also want to prevent duplicate tasks from being performed in the case the system calls view will appear while a task is already in progress. because we are in view will appear and not view did load, and so view will appear can be called more than once. And so this is what a task handle looks like. It's a type with two generic arguments. First one is the return type. Second one is the potential error type. And so when you have a task that doesn't return anything, the return type is void, and that never produces an error, the error type is never. And sometimes in your code base, it might make sense to create a type alias so that you can refer to this type more easily than by explicitly providing these two generic arguments each time. And so here we are storing the handle to the task, so full optional, because the task might not always be running, and so we want to have nil as both the default value, but also the value once the task has either been finished or cancelled. And so now what we do is that in view will appear, first we test if the loading task is not nil. If it's nil, we just return. We don't create a duplicate task. Then we create the task. So we create the task through the task initializer, just like before. But this time, we store the result inside the loading task property. And at the end of the code, inside the closure we pass to the task, we set the task back to nil, so that once the task is over, we remove its handle. There are cases where we might want to still keep the handle around, especially when the task has a return value, because we might want to access the return value later. But here that's not the case, so we want the handle to go away so that we can then trigger the task another time if need be. And in view did disappear, what we want to do is call cancel on the task so that we ask the task to cancel. Maybe it will go about it later, but I just want to say it in case. In Swift concurrency, task cancellation is a cooperative mechanism, meaning that when you do cancel, it's not like if you were like killing a process, you're actually asking the task to cancel, and the task can check if it has been asked to cancel. The idea behind it is that you don't want to force kill a task because the task might be in the middle of a critical operation, like writing to a database or writing a file, and you don't want to kill the task midway because it would create like probably some corrupted data. So what cancel does is telling the task, please cancel, and the task can check regularly if it has been asked to cancel, and if so, exit. Loading task. I think a comment. So is that an error? Loading task different of nil? Let's see. So if you're talking about this part right here, so here it's not testing for an error, it's testing. Oh, okay. I think you're saying like if you do loading task different of nil to decide whether or not a loader should be shown. So yes, that would be then the right way to plug the handle to the task, the handle we keep of the task with the state of the loader, and I guess the rest of the article is going to go over it. Here we have a part about the two generic types of tasks. So let's see what it has to say. So note how a task has two generic types. The first indicates what type of output that it returns, which is void in our case, since our task simply forwards its loaded user model onto our view controller's methods. And the second is for its error type. And since we handle all errors within our task itself, that error type is never in this case. Calling the cancel method on a task also marks all of its child tasks as cancelled as well. So by cancelling our top level loading task within our view controller, we are also implicitly cancelling its underlying network operations at the same time. However, know that it's up to each individual task to implement the actual cancellation handling code required to cancel its particular operation. So what I was referring to by saying that cancellation is cooperative. So even though the system will automatically manage and propagate cancellation in terms of marking, it's up to each task to decide how to actually handle that cancellation if it wants to. It is also absolutely free of ignoring the cancellation. And the way to do it is by calling task.checkCancellation within the code of the task. Context inheritance now. The relationship between a given task and its parents can be quite important, at least within @main actor marked classes, such as views and view controllers. That's because child tasks are not only connected to their parents in terms of cancellation, they also automatically inherit the same execution context as their parent uses. To illustrate when that behavior can become somewhat problematic, let's imagine that our profile view controller was loading its user model from a local database rather than over the network, and that our database API is completely synchronous. At first glance, it could seem the following implementation will be completely fine, since we might expect that our asynchronous work will still be executed on a background thread, even if we no longer perform any await-based calls within our task. So the idea is that this call to the database loads the model. However, this is an expensive call that is synchronous. So this code will block its thread until it has finished. And when writing this code, I guess we sort of like naively think that because we are in a task, we are guaranteed that this code will run on the background thread, and so it's perfectly fine to block a thread as long as it's not the main thread. However, although the above task will indeed be performed asynchronously, it will still be executed on the main thread since it's being dispatched using the main actor. It inherits the context from the viewWillAppear method that it was created in. So essentially, our above task is more or less equivalent to performing the same database call within a dispatch queue main async closure. And so the task is not performing what we might have been expecting it to. As John is saying, the task here is conceptually equivalent to calling dispatch queue main async. So the code is still run asynchronously, so not in this run loop iteration, but it is still run on the main thread, which is not what we want. Since we probably want to move our database call away from the main thread to prevent that call from interfering with the responsiveness of our UI, we could instead use what's called a detached task, which will be executed within its own standalone context. When doing so, we'll also have to use await when calling back into our view controller's method, since those methods are isolated by the main actor. We can also no longer set our loading task property to nil directly within our task, because we are now in a detached task, which is different than the context, which is executing in a different context than the one defined by the call to viewWillAppear, which was happening inside the main actor. And the main actor, I didn't say it, but main actor, you can basically understand it as like the main thread. It's the actor that protects, that wraps the main thread. So here with task.detach, this time we are creating for real a background. We are making sure that the closure we pass will run on a background thread because the task is now detached, so it's independent from the main actor. And you can see that this time we also need to capture a weak reference to self, because the closure we are passing to this task is now completely independent from the context in which viewWillAppear was called. And we also cannot no longer directly set loading task to nil. We need to call a method on self, which in turn is calling loading task. And you can notice that all of the usage of self needs to use await. That's because self is bound to the main actor through its inheritance of UI view controller. And since the code that the detached task executes is no longer executed on the main actor, we need to wait in order to be able to switch back to the main actor. And so that's why we have to use the await keyword, because at the moment when we call this method, the main actor might not be available, and so we might need to await until the main actor is available, for instance, when the current run loop iteration has finished. And indeed, there is another syntax where you can do task and then at main actor in order. So I guess here your idea would be to create a new task inside the detached task in order to have the part where you can directly set the loading task to nil. Oh no, I think you mean the other way. If you want, so here with task.detached, we are able to create an execution context, an async execution context outside of the main actor when initially being on the main actor. And if you were on the other way, initially outside of the main actor, then you want to create a task with this at main actor in annotation. Typically, imagine that, I don't know, like in your view model, you have some code that uses a closure, and you want to set some properties that are at published, for instance. Then I guess this would be a good example to create a task that is at main actor. And that's something that I've used and I've seen being used quite a lot at work, because it's indeed very handy. And still better than calling dispatch queue main async, because you are still in a place where you can also call like other asynchronous functions. By the way, when we say updating UI elements, it means UI kit objects, so UI label, UI image, all these kind of things. But it's also true for add publish properties in SwiftUI. They are easy to forget, but usually the crashes that you will get will remind you of that very quickly. In general, it's recommended to only use detached task when we explicitly want to create a new top-level task that uses its own execution context. In other situations, simply using task to encapsulate our asynchronous code is the recommended way to go. And to tell you honestly, I don't think I've ever used a detached task in production. I've used it like when writing like code examples for videos, but I don't think I've ever needed to use it in production, because it's for quite specific use cases. And the example John has is great when you need to call like a existing blocking APIs. It's a great example, but yeah, it's mostly like when wrapping existing code. But besides that, most of the time you create a task and that will do what you expect. Next part is about awaiting the result of a task, because up until now we've only seen tasks that that were doing side effects, but a task can also return a value. So finally, let's take a look at how we can await the result of a given task instance. For example, let's say that we wanted to extend our above database-based view controller implementation with support for loading the current user's image over the network. To do that, we'll wrap our detached task within yet another task instance, and we'll then use the await keyword to wait for our database loading operation to complete before proceeding with our image download. Something like this. So we have added an image loader. Inside the loading task, so it's a task, this time it's just a regular task. We create a detached task, which we store its handle inside the local constant. And then we do an await on the value of the task handle. And then once we have the user, then we get the image URL from the user to perform the next network call. So you can see here, it's a good example of a place where you could not use async-let instead of just making the call sequentially, because in order to make the second call, you need the result of the first one. So it's a good example, by the way, of a place where async-let would not be possible, because the code here the calls are sequentials because they need to be sequential, because the second call depends on the result of the first call. And so we can note how we can once again call our view controllers method directly within our top level task, because the top level task is main actor bound, since exactly what I was saying, just like before. That illustrates just how smoothly we can now mix work that's performed both on and off the main queue without having to worry about accidentally performing UI updates on the wrong thread. And typically also, when you call like URL session .share.data, you can imagine that later inside the way it's implemented, it switches to either a detached task or explicitly to a background thread, but at some point there is a switch made in order for the network call not to happen on the main thread. You're saying putting a task in another task has the same code smell as Pyramid of Doom. That's a very good question. I would say it's probably not the best approach, but I wouldn't say it's as bad as a Pyramid of Doom, because the big problem with Pyramid of Doom is that I'm trying to find a way to phrase it, but basically, since your task takes no argument, the it's less obvious to make the inner task rely on the way the outer task is implemented. So I agree, it's not the best way to do it. And here I think it's an example, but in real life, honestly, I've never needed to write this kind of code, because most of the time your database would be encapsulated into a service, and so there would be more like APIs in the middle to make things more like separated. But I would say indeed you don't want to be nesting tasks into each other, especially since there is no real need. The only interest of nesting tasks is to be able to switch on and off the background. But if you want to run several operations in parallel, you can use, or rather concurrently, you can use async-let. You don't need to create two tasks inside the parent task. So I agree with you that it's a code smell, but it's not as bad, I would say, as when you do it with closures, especially because there are better ways to avoid it. But definitely, by default, what you should do is by default try to make your call with await. Use async-let if it makes sense, and if you need to, then create a task. But don't create a task within another task by default, because 90% or 95% of the time, this is not the solution you want to choose, and there is a better one. And so this dot value is a property that is defined on the task handle, and that you can await in order to have the value returned by the task. And so here, the value, actually here there is an implicit return that is not written, but what happens is that the closure you pass to a task can return something, and then you can retrieve that thing by calling the value on the task handle. And of course, you need to await, because the task needs to finish in order for the value to be readily available. Okay, and so this illustrates how smoothly we can now mix work that's performed both on and off the main queue without having to worry about accidentally performing UI updates on the wrong thread, because that part is being checked by the compiler. Because if you are not on the main actor, the compiler will force you to await in order to access the view controller. And if you can access the view controller without awaiting, then it means that you are in a context that is main actor bound. Conclusion, so we're reaching the end of this penultimate article. So Swift's new task type enables us to encapsulate, observe, and control a unit of asynchronous work, which in turn lets us call async marked APIs and perform background work, even within code that's otherwise completely synchronous, so typically all the lifecycle methods you would find in UIKit. That way, we can gradually introduce async functions and the rest of Swift's new concurrency system, even within applications that weren't designed with those new features in mind, so typically a UIKit application. And I definitely recommend that you read, that you wander around John's website, because there is great content, as I was saying. I especially recommend that you check out the Discover page, because you have some great guides to get started with the main technologies that are required in order to do iOS app development. And now we move to the last article I have for this live stream, which is about understanding Swift task groups with examples. So task groups, they were the last not keywords, but the last code, the last identifiers, the last type that I had put on the thumbnail. So we've seen async await, we've seen task, we've seen async-let. Now we see task group. And remember, I've told you earlier that async-let, you can only use it when you have a static number of child async function that you want to run concurrently. As you can imagine, task group is what you use when you have a dynamic number of async operations that you want to run concurrently. So this time we are on a website called Swift Senpai. Once again, you have all of the links in the description. And the article is called Understanding Swift Task Groups with Example. So Apple introduced task groups in Swift 5.5 as one of the essential parts of the Swift concurrency framework. As the name implies, a task group is a collection of child tasks that run concurrently and only returns when all of its child tasks finish executing. So we can see a parallel with async-let, where not the task but the calls would happen concurrently, and we would then wait in order to wait for all of them to finish executing. And so in this article, I would like to show you how to create a task group, add child tasks to a task group, and gather results from all the child tasks. That's a lot of topics to cover, so let's get started. And by the way, this article was written in 2021. I think there have been a few new convenience APIs added to task group, I think especially this year. But once you've understood like the basic principle, these new APIs are very easy to understand on your own. So let's get ready. As usual, I will use some sample code to explain and help you to understand how task groups work in Swift. Before diving into task groups, let's first define an operation struct that we will use throughout this article. So it's a struct called slow divide operation. It has a name, two doubles, and a sleep duration. And what it does is sleep for an amount of time and then actually perform the operation, so perform the divide operation. When I was saying there are newer APIs in Swift, now you can use a version of sleep where you pass in an enum with a stated value to specify which unit. So here, what's always a bit weird is that task.sleep takes a number of nanoseconds. So you need to pass in here billions of nanoseconds to have 1 billion of nanoseconds is 1 second. But now you have an API where you could say task.sleep.second and then 1 second, which is more readable and less error prone. So the slow divide operation is a simple struct that contains an execute function that performs a divide operation based on the given numbers. Note that I purposely slow down the execution by making it sleep for a certain amount of time before dividing the numbers. This gives us good control of how long the divide operation should execute, therefore allowing us to easily observe what really happens when multiple slow divide operations run concurrently in a task. And indeed, it's a great way if you want to prototype how concurrent calls are running together. It's a great way to implement something that resembles a network call, but it's still simple enough that you can easily debug it and understand what is happening. You could even imagine passing in, you can actually pass in the sleep duration because it's an argument. So this way you have complete control over how long it will take. Okay, with that out of the way, let's dive right into task groups. So in order for us to be able to use task groups correctly, there are a few task group behaviors that we need to be aware of. A task group consists of a collection of asynchronous tasks, child tasks, that is independent of each other. So we can see the same ID, the same requirement than for async-let, which is that all of the concurrent calls have to be independent from each other, meaning that the call number 3 doesn't depend on the result of call number 1, that kind of thing. You can also see the word collection here, which kind of hints at the fact that we're going to deal with a dynamic amount of values, just like a regular collection in Swift also allows us to deal with dynamic amount of values. All child tasks added to a task group start running automatically and concurrently, just like async-let. We cannot control when a child task finishes its execution. Therefore, we should not use a task group if we want the child task to finish in a specific order, just like with async-let, even though you can still get around it by maybe splitting your code into 2 different task groups and having one be defined before the other. A task group only returns when all of its child tasks finish their execution. In other words, all child tasks of a task group can only live within the scope of their task groups. A task group can exit by either returning a value, returning a void. So if, for instance, all the tasks were only implementing side effects, or throwing an error. And now that you have learned how a task group behaves, it's time to write some Swift code. So let's create a task group. To create a task group, we can use the with task group of returning body or with throwing task group of returning body functions introduced in Swift 5.5. So we can see a similarity with the continuation in the sense that we have two different APIs depending of whether or not our asynchronous call will be throwing errors or not. Since the task group that we want to create will not throw any error, we will be using the with task group of returning body variant in our sample code, which is also a bit simpler. So I guess we can make the code a little bit more like concise and easy to read. But the ideas between throwing task groups and non-throwing task group basically translate to one another. So it takes the following form when being called. So the first argument is the child task return type. Returning is the task group return type, and the closure where you will be creating the task. And you can see that in this closure, you have access to the task group passed as an argument. So the idea is that typically, let's imagine that our task group is supposed to fetch several UI images. It would be a task group of UI image.self because each task will return a UI image, and the task group itself would be returning an array of UI image because here we want to collect the image in an array, but you could imagine, for instance, all of the task group return a number, and the task group itself, all of the tasks return a number, and the task group itself also returns a number because the task group is returning the sum of all the numbers returned by the child task. So there is no strict rule, no like predefined rule between the relation between the return type of the child task and that of the task group returning type. It really depends on what you need, but most of the time it will be either aggregating data into a collection or aggregating data into like a computed result. It's often this kind of pattern that emerge, but if you need something else, you are free to implement it. So in our example, we will create a task group that spawns multiple child tasks that execute a slow divide operation and return its name and result. When all the slow divide operations finished, the task group will collect all its child task results and return a dictionary consisting of all the slow divide operation names and results. So quite similar, for instance, if you were passing in an array of user ID, making a call to retrieve the detail of each user, and then returning a dictionary of the ID as a key, the user ID as a key, and the user detail as the value. We'll see it's important because, as we're going to see later, the order in which the task group return its value is not the order in which the child tasks were created. That's why most of the time you want to have a dictionary in order to know which results corresponds to which input. But let's see if we'll probably explain a bit later. So with that in mind, we can create a task group using the function with task group by saying, okay, let's await with task group because this will await until the task group has finished executing. And so we create a task group of string double, so a tuple. So each child task will return a tuple containing a string and a double. And the task group itself will return a dictionary that will have for keys strings and for values doubles. So all results here will be of type dictionary string to double. And then we have the body where we can use the task group to spawn child tasks. So notice that the instance of task group is given to us as a parameter of the body closure. In the next section, we will take a look at how we can leverage this task group instance to spawn multiple child tasks that run concurrently. All right. So the task group in action. Let's say we have an array of slow divide operation as shown below. So we have an array of 3 operations taking different amount of time, one taking 5 seconds, another one 1 second, and the third one 3 seconds. Then we can add child tasks to the task group by looping through the operations array. And this is the pattern you will see most of the time. Inside the body you pass to with task group, you will iterate over some kind of collection, because remember, when you need a task group, it's because you need to deal with a dynamic number of input, and usually a dynamic number of input will be provided through some kind of collection that you will need to iterate on. So here we iterate over all of the operations. And for each operation, we add a task to the task group. So just like we would create a task, is the same ID. We define a closure, and except that instead of being a standalone task, it's a task being added to the task group. And so we execute the slow operation. We can use await inside this closure because it's an async closure. Once again, just like the closure we passed previously to the task initializer. And then we return the child task result, so a tuple of a string and a double, just as we've said here in the signature of the function. And the reason why I guess we had to explicitly declare the type here is because I guess Swift is not able to infer from this statement here the type at this level right here. Maybe it was maybe it's one of the things that were added with the latest version of Swift, but I'm not sure. I think what they added were some convenience versions. For instance, I think what they added is when you are making a task group that returns void, then there is a little bit of a nicer API. I think that's what they added this year. So one thing worth mentioning is that we are returning a tuple of string and double in the child task operation closure, which matches with the child task result data type we set early on. So exactly what I was saying. That's the pattern with this live stream focusing on articles, is that I always say what the article will say just after. But that's interesting because at least if I make a mistake, I have a safety net to catch me a little bit later. So it takes some of the pressure off for me. One thing worth mentioning, no, that's what I've just read. So it's the same data type, okay, what we were saying. As mentioned earlier, all child tasks will run concurrently and we have no control over when they will finish running. In order to collect the result of each child task, we must loop through the task group like so. So this code right here is going to happen after the first for loop. So inside the body you pass to a function, you will very often have this pattern of first you iterate over the collection of inputs in order to create the child tasks, and then you iterate over the results in order to collect the results. And the way it's done is that we create the structure that will gather the results together. So string, dictionary of string and double. I see a few people in the chat. Welcome. Hope you enjoyed the content. We are near the end of the live, but don't worry. A replay will be available as soon as the live finishes. So we create a structure that will gather all of the results, and then we iterate over the results of the child task in the task group, and we use a for loop, but a slightly different one, because to iterate over a regular collection, we use a for in a loop, and here we use a for await in a loop. That's because task group is an async sequence, and so we need to use for await because we need the result to be ready in order to retrieve them, and so we need to take care of the case where it's going to basically we need to have the await keyword in order to highlight the fact that between two iterations of the loop there might be a suspend point, because we need to wait for a new child task to complete in order to have a new value, a new result value to iterate on. But besides that, it's the same logic than a regular for loop. And what we do is that on the dictionary, we use the result, which is a tuple, and we use the first member of the tuple for the key to set in the dictionary, and the second member of the tuple for the value to set. And finally, we return child task.results. And I'm sure it will say it later in the article, but you can notice that the type of what we return matches what we had promised here that the task group would return. So let's see what the article says. Notice we are using the await keyword when looping to indicate that the for loop might suspend while waiting for the child task to complete. Every time when a child task returns, the for loop will iterate and update the child task results dictionary. Once the child task completed execution, once all the child tasks completed execution, the for loop will exit and proceed to return the task group result. As you might have noticed, the data type of child task results must match with the task group result defined that we previously set. So exactly what I was mentioning. Okay. So we can see that same data type in all three places. Pro tip, use void.self as the result type if you have a task group or child task that does not return a value. Typically, if you have several files and you need to save them locally, this would be a typical example of a child task that would return void. And as I was saying, I think there is a nicer API for this special case in the most recent version of Swift. Before taking our sample code for a spin, let's add some print statements before and after we trigger a task group to inspect the final result and the time required to execute all child tasks. So here's the full sample code. So it's what we've seen. Just see that there is a print statement to say, okay, we have started with the current date. And there is a print statement here to say, okay, this is when it has ended. And here are all the results. And so normally the task group should take to execute the time that the longest child task took. So it should take something like 5 seconds to execute. We'll see if my assumption is correct or not. If we try to execute the code above, the output we get will be something like this. So we can see that there is indeed 5 seconds that have elapsed between start and end. And then we have the result. And we can see that in the result dictionary, the order is not the same than the one we had in the input dictionary. So as you can see, the entire task group took 5 seconds to complete. The fact that 5 seconds is also equal to the longest sleep duration among all the slow divide operation, indicating that all child tasks do in fact run concurrently, because if they were to run sequentially, then it would have taken 9 seconds, because it would have been all of the sum of all of the durations. I'm just noticing that it's past 10 p.m. for me in France. So after a day of work, that's the point where I'm starting to feel that I'm a little bit tired. I'm also glad we are closer to the end of the live stream than at the beginning, when I get tired like that. Because it's the moment where I start to confuse words, and it's never a great thing, especially when the goal is to teach new concepts to beginners. And I see a very good remark in the chat: new algorithm to sort numbers. Yes, if you're given an array of integers and you implement a sleep for each of the integers, it will have the side effect of actually sorting the integers, because you can see that we have the first operation here, then we have the second operation, then the third, then the first, and indeed they are in ascending order. So this is the most inefficient way, I think, to sort integers. It's the most stupid way to sort integers, but it's a nice fun fact that you can use the sleep function to sort integers. Okay. And if you take a look at all results, you will notice that it contains results of all the child tasks. This further proves that a task group only returns when all of its tasks finish running. This also indicates that the child task can only live within the context of a task group. So once the task group is over, the task group is also over. So you have a link to the sample code that you can download if you want to try it. And I don't think the article says it, but I want to say it once again. The fact that the order of the keys when we print the dictionary is not the same than in the array is not a coincidence. It's because the tasks, the results were added to the dictionary in the order in which they were produced. And so this for loop here didn't iterate over the same order than this second for loop. Here we iterated in the order of the inputs, and here we iterated in the order in which the tasks have completed. And so be careful if you were to collect the results into an array. You might be tempted to think that you can just use the index of the input to retrieve the output. It won't work because of that, of what I've just said, of the fact that you iterate over the results by the completion order of the child tasks and not by their creation order. And so most of the time, when you are using child tasks to return results, you will often have this pattern where you will return a dictionary matching either the original input or an ID of the original input with the actual output. This way, in the end, you can subscript the result and say, hey, I want the result for this specific input and not just whatever result was returned first, because it's probably not something that your app wants to rely on. So it's one of the big caveats of using task groups, especially because in the API and in the compile time safety that it brings, there is nothing to warn you about it. So be careful about it, and most of the time you will end up returning dictionaries. Also note that there is no way to say how many child tasks should execute concurrently. You cannot say, I want to execute at the maximum of 4 tasks concurrently. The best you can do is create sequentially groups of 4 tasks, but you will still need the first batch to finish before the next batch can start. You don't have something with kind of like an executor pool logic where you could say, okay, I want to be able to run 4 child tasks concurrently, but no more. And so as soon as one of the 4 running tasks has finished, you start another one. You don't have this, and it can be some kind of a limitation depending on your needs. I'm sure there are ways around, but at least with the built-in API you get, that's a limitation to be aware of. Let's just read the conclusion. So to wrap up, in this article, I have shown you how to create a task group, how to add a child task to a task group, and how to gather results from a task group's child task. In my next article, I will talk about error handling in task groups. Stay tuned. And so I would definitely recommend that you read this other article, and also like the rest of the content on this blog, because it's also a very good source of information to learn about Swift and iOS. And that was actually the last blog article I had for you. So we have reached the end of this live stream. Thanks a lot for following it. I'm very curious if you have any kind of feedback on this new format, which is to gather existing resources in order to kind of like teach all of the main concepts of a part of iOS development. We could say it was the first time I was doing it. I had already done the concept of a live newsletter where I would read and comment articles, but it was not focused on a specific topic. First time I do it this way. Personally, I have a lot of hopes for this format because I think it can do a great job at like giving this like very like comprehensive picture of how to approach a new technology, a new part of iOS development. At least after what we've covered in this live stream, I feel like someone that is getting started with iOS and has seen all of these examples being structured in different ways. I think it gives you like some good pointers to keep on and basically get started writing your own code. So if you have any feedback, please feel free to write it in the comments or to tell me like on Twitter, on LinkedIn, wherever. I'm super curious to know about it. If you have ideas for other topics that I could also cover with this format, same thing, please let me know because I would really like to do this format again. And I think it's the moment for me to finish the live, maybe soon to go to bed, actually, because it's more than 10 p.m. in France, and I can tell you I'm starting to feel a bit tired. But thankfully, I'm not working tomorrow, so I don't have to worry about being energetic tomorrow. I can just chill. But once again, thank you for attending. I hope you've enjoyed this live stream. More importantly, I hope you've learned things that you will be able to use in your daily job. And as always, thank you for watching. See you next time. Bye bye.